All right, geometry students, today we are moving into our lessons about relationships within triangles, and we're going to start with perpendicular and angle bisectors. We should be able to use properties of perpendicular bisectors and angle bisectors to determine side lengths in triangles. So in this lesson, we're going to talk about the associated theorems and work on some application practice. Make sure that you're following along with your guided notes, and let's get started. So first, let's just talk about what a perpendicular bisector even is. So we can see here in this diagram that line CD is a perpendicular bisector because it's cutting in half one side of the triangle at a 90-degree angle. So the line is perpendicular to the base of the triangle. It cuts the base into two congruent parts. So let's talk about the perpendicular bisector theorem itself and what it means. So we're saying that if a point lies on the perpendicular bisector of a segment, in this case CD, then it is equidistant or equal distance from the endpoints of the segment. In shorter terms, if line CD is perpendicular to segment AB in the triangle, and we know that AD is congruent to BD, meaning it's been bisected, then we know that side AC is congruent to side BC. So AC is congruent to BC, is what we're saying here. The converse of the perpendicular bisector theorem, we know that converses pretty much say the same thing but backwards. So if a point is equal distance from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So basically we're saying if CA is congruent to CB, then we know that line CD, the line we have going through the triangle, is perpendicular to segment AB. And we know that AD, segment AD, is congruent to segment DB. So let me just label that here. We said that if CA is congruent to CB, we know that CD is perpendicular to AB, and we know that segment AD is congruent to segment DB. So it's pretty much saying the same thing backwards. All we needed to know for this one is that we've created a perpendicular bisector. These segments are now congruent to each other. So let's put this into practice. We are going to use the information given in the triangles to find the values of variables. We're going to be putting in some algebra practice. So we're given this triangle, and it appears that the segment running through the triangle has cut the base of the triangle at a right angle, and the base is cut into two congruent parts. So this segment is a perpendicular bisector. And if it's a perpendicular bisector, our theorem says that these two segments here are congruent. So we can write the equation 7x plus 24 is equal to 13x minus 48. And from here we can solve. I'll do that pretty quickly here. Subtract 7x from both sides. Add 48. And x equals 12. For the second application here, we are given that the sides of the triangle are congruent to each other, and we know that this segment running through the triangle is forming a right angle with the base. So using the converse of the perpendicular bisector theorem, we can say that these two portions of the base are congruent to each other. So 17x minus 3 is equal to 9x plus 13. And here we go, we can solve, subtract 9x from both sides. We get 8x minus 3 equals 13. We're going to add 3 to both sides of the equation. We get 8x equals 16. Divide both sides by 8, x equals 2. For additional practice with applying the perpendicular bisector theorem and converse, go ahead and try out problems 3 through 6. Now let's move into angle bisector theorems. Here's a different situation. We are saying in both of these diagrams that angle BAC is being bisected or cut in half. And we're saying here that if a point is on a bisector of an angle, we're talking point D here, then the point is equal distance from the sides of the angle. So in this case, if ray AD, the bisector cutting through this angle, if it bisects angle BAC, if it cuts it in half, then we are saying that ray AB is perpendicular to segment BD. So ray AB here is perpendicular to segment BD. And we're saying that AC, poorly drawn there, is perpendicular to segment CD. So if that is all true, then we know that the two portions of these triangles here are also congruent to each other. We're saying that BD is congruent to DC. And then the converse, saying the same thing but backwards. If a point is on the inside or interior of an angle, and it's equal distance from the sides of the angle, so we're basically saying if BD is congruent to CD, then we know the point is on the angle bisector. So in other words, if BD equals CD, if this is true, and if we know that ray AB is perpendicular to segment BD, and we know that ray AC is perpendicular to segment CD, then we know that ray AD, the ray going through the main angle, we're saying this bisects angle BAC. And it also means that angle BAD is congruent to angle CAD. So we're saying that each part of this main angle is congruent. So let's try applying that information. We're going to look at problems 8 and 9. So we are given that the main angle has been cut in half. Both parts are congruent to each other. We're also given that the sides form a right angle with the segments. So with that being the case, we can confidently say that this 4x plus 30 segment would be the same length as the 9x minus 5 segment. We're saying they're congruent to each other. So we can write an equation and set that up. 4x plus 30 is equal to 9x minus 5. And we can solve for x. Let's subtract 4x from both sides. we get 30 equals 5x minus 5. Let's add 5 to both sides. We get 35 is equal to 5x. And divide both sides by 5, we get x equals 7. And in the other instance, we're looking at the converse of our angle bisector theorem. So we are saying that if these two segments are the same distance from this point and they form a right angle with the outer rays, then we can say that the angle has been bisected. So if the angle's been bisected, that means each part of the angle is congruent to each other. So we're saying that 5x minus 11 is equal to 8x minus 41. And from there, solving the equation, negative 11 is equal to 3x minus 41. Let's add 41 to both sides. And we get 30 is equal to 3x. And we get x equals 10. So the value x equals 10 would satisfy the converse of the angle bisector theorem. For additional practice, try out problems 10 through 12. And that is it for this lesson about perpendicular bisectors and angle bisectors. Thank you so much for watching. Make sure you try out the additional practice problems and check your answers with my filled in notes later. Ask for support if you need it, and I hope you have an awesome day.